After learning how to differentiate functions, we move on learning on how to take the derivative of parametric equations. Welcome to differential calculus. What are parametric equations? These are equations or functions which are written as a function of another variable. For instance, we have x as a function of t, and y also a function of t. The variable t is called parameter, and in parametric equations, the usual parameters used are t and theta. Let's have an example. Say x is equal to t, then y is equal to t squared. Let's use a table to find values of each variable. Take note that t is the independent variable, and both x and y are the dependent variables. Assuming t of -3, x turns out as -3, and y is 9. When t is -2, x is also -2, and y is 4. At t of -1, x is -1, and y is +1. At t of 0, x is 0, and so is y. Then when t is 1, x and y are also 1. At t of 2, x is 2, and y is 4. And if t is +3, x is 3, and y is 9. Connecting the dots in the Cartesian plane, we can identify the curve. How about taking the derivative of parametric equations? How do we come up with the first derivative, which is dy over dx, when the functions are in terms of t? There are two methods we can come up with the derivative. First is through derivatives. Having two functions, x and y, take the individual derivative of each function. Take note that since they are both functions of t, the derivatives turn out as dy upon dt and dx over dt. If we take the ratio of dy over dt with dx over dt, we can then eliminate dt, which then results to dy over dx. The other method is through differentials. Having the two functions for y and x, take their separate differentials. Dy is then equal to the prime of the equation with dt. Then dx is the prime of the function times dt. Next is to take the ratio of dy over dt, where the dt's at the end also cancel out, leaving dy over dx. For the second derivative, we continue differentiating what we just got as dy over dx. However, take note that when we differentiate dy over dx, it is with respect to dt, as the function is in terms of t. So what we end up is the second derivative of y all over dt dx. So in order to have d of x squared in the denominator, we multiply the reciprocal of dx over dt. This also eliminates dt from the equation, and having the second derivative of y with respect to x. The first example includes the two terms x, which is 3 times the square of t minus 2. Then y is equal to 9t squared plus 4. Let's take dy over dx and dy squared with respect to x. For the first derivative, we start by differentiating each function. With x equal to 3 times the square of t minus 2, the derivative is with respect to t. Dx over dt then starts with 3 times the derivative of the square of the binomial, which uses general power rule, and that is the exponent 2 times the binomial t minus 2 raised to 1. Then with chain rule, take the derivative of each term in the binomial, which marks d of t over dt and the derivative of the constant 2. dt over dt is 1, and the derivative of 2 is 0, making dx over dt as 6 times the binomial t minus 2. For the y function of 90 squared plus 4, take the derivative with respect to t, thus having the constant 9 times 2t, then attach the derivative of t with respect to t through chain rule. The second term is the derivative of 4 with respect to t. dt over dt can be reduced to 1, and the derivative of a constant is 0, so dy over dt is 18t. Now taking the ratio of these two functions, we have dy over dt all over dx over dt, and placing the derivatives, 18t all over 6 times t minus 2. We can note that dt's cancel out, and 18 and 6 can also be reduced, leaving dy over dx as 3t over t minus 2. Now let's solve for the second derivative of y with respect to x. We left off with dy over dx as 3t over t minus 2. By taking its derivative, we end up having d squared y over dt dx. This happens as we are taking another derivative with respect to t again. The function requires quotient rule, where the denominator becomes the square of t minus 2. Employ low d high minus high d low in the numerator, making t minus 2 with a derivative of 3t minus 3t times the derivative of t minus 2. At this point, we only simplify and eradicate the d over dt's. From the second term, distribute d over dt among the terms of t and negative 2, making the numerator 3 times the binomial t minus 2, then dt over dt, minus 3t with d over dt of t minus d over dt of 2. dt over dt is 1, and the derivative of a constant is 0, simplifying the whole function into 3 times t minus 2 less 3t over the square of t minus 2. When 3 is distributed, we end up with 3t minus 6 less 3t, which can then be simplified, making the function as negative 6 over the square of t minus 2. Now is the time to multiply the reciprocal of dx over dt, which is 1 over 6 times t minus 2. This cancels out 6, giving the final answer for the second derivative of y with respect to x as negative 1 over the cube of t minus 2.